In this tutorial, we will be discussing hybridization and valence bond theory. Hybridization is about the center atom's atomic orbitals undergoing a transformation to accommodate electrons from other atoms to form bonds. Hybridization type corresponds to the electron geometry or the family of the compound. So we're talking about tetrahedral or octahedral, stuff like that. Remember, the electron geometry was determined by the number of attachments and non-bonding electrons around the center atom. So the number of atoms that's attached to, and the number of lone pairs, or non-bonding electrons. So when we're talking about the electron geometry, we're referring to linear, trigonal, planar, tetrahedron, etc. And then the corresponding hybridization that goes with it. For instance, if something has a triple bond, it's going to have an sp hybridization, which means one s orbital and one p orbital are blending together to create two new orbitals. Or a double bond could fall under the category of sp2. That's not the only type of trigonal planar, but it could correspond. So one s orbital and two p orbitals are blending together. So let's take a closer look at sp2 hybridization when seen in a double bond. So a double bond, as you know, has 4 electrons or 2 electron pairs. Not all elements can form double bonds. Elements that can double bond with themselves or each other are carbon, sulfur, nitrogen, oxygen, and phosphorus. Also remember, just like we talked about in the previous tutorial when we were talking about the difference between sigma and pi bonds, that a double bond has both sigma and pi. So it does have one overlap of either p orbitals or s orbitals where they're actually overlapping, and then a pi component where it has a top and a bottom. Sigma bonds are electron density within the plane of the bond, while pi bonds have the electron density above and below the plane of the bond. So, sp2, that means we have one s orbital and 2 p orbitals that are coming together and blending to create 3 new orbitals that are considered to be hybridized. And when we put them together, they form this triangle that you know as trigonal planar. So how exactly does this work with a double bond involved? Formaldehyde is an example of this. Notice it still has the three bond attachment configuration where it has a triangle. So we have 2s2, 2p2, 2s2, 2p4, and 1s. 1s1 for hydrogen. Well, what's happening is that the one s orbital and 2 of the p orbitals are blending together. So 2s orbitals and 2 of the p orbitals are blending together to be a 2p2 orbital. 3 of them. And then this one that was left over is still there. So the center atom in the molecule is carbon. Its atomic orbital needs to undergo hybridization. So we're talking about hybridization, we're talking about specifically the center atom. The center atom is what's going through the hybridization. The unused p orbital on the carbon contains an electron, and is in this p orbital overlaps the p orbital of the oxygen atom to form the pi bond. And remember, in order to have a pi bond, you have to have p or d orbitals for this overlapping part here. So when we're looking at this coming together, we had sp2, meaning one s orbital and 2 p orbitals are coming together to form 3 sp2 orbitals. And then we also still have a p orbital here that was not overlapped. So here is our p orbital that did not overlap, that didn't hybridize. So that means that these p orbitals can then overlap on the top and the bottom. And these three here are your three sp2 orbitals that are overlapping to form sigma bonds. So degrees of rotation, what it's referring to when you read about degrees of rotation is talking about if we'd had the two carbons bonded together, if we could rotate one in one direction and rotate the other in another direction. Can they rotate freely? The more electrons between the two atoms in a bond, the more restrictive the rotation is. So a single bond you can rotate very easily, but as it gets to double and triple, it becomes more difficult. Bonding orbitals that form the sigma bond point along the internuclear axis. The rotation around the bond does not require breaking the interaction between the orbitals. However, the bonding orbitals that form the pi bond interact above and below the internuclear axis. So rotating around the axis requires the breaking of that interaction in order for it to rotate. So it's not going to rotate nearly as well. And it gets even more difficult when you have another set of pi interactions for the triple bond. So let's take a look at that triple bond. As you know, triple bonds have 6 electrons or 3 electron pairs. Not all elements can form triple bonds. Elements that can triple bond with themselves or each other are carbon, sulfur, nitrogen, and oxygen. And remember that they have to have sigma and pi components in order to do that. And sigma bonds, once again, are electron density around the plane of the bond, while 2 pi bonds, the electron density are above and below the plane of the bond. So we're looking at the center atom when we're talking about hybridization. So the center atom uses hybrid orbitals to form sigma bonds or lone pairs. And it forms pi bonds from 2 sets of non-hybridized p orbitals. The electron and molecular geometry is typically linear in a 180 degrees bond angle. So when we're talking about a triple bond, we're talking about one 2s orbital and one 2p orbital. So one s and one p coming together to form 2 sp orbitals. As a result, you still have 2 p orbitals that are not hybridized that can then form that multiple bond. So the carbon, once again, is the center atom that we're concerned with. We have the 2s2, 2p2 here. One of the s orbitals and one of the p orbitals are going to come together to hybridize. And then we still have 2 p orbitals that did not hybridize. So that sp is what's forming the sigma bonds. And then the 2 p orbitals are the one going up and down and at us and towards the screen. So let's move on and do sp3d hybridization with trigonal bipyramidal geometries. The center atom has 5 electron groups, or lone pairs and or atom groups around it. So the molecular geometry in this location is trigonal bipyramidal, which is what we see here. Seesaw, which is if one of these had a lone pair. T-shape, if another one of these had a lone pair. And linear, if we had 3 lone pairs on there. The center atom uses d orbitals from the valence shell for hybridization. The d orbitals can be used to make pi bonds as well. So we have an atom here that has one 3s orbital, 3 3p orbitals, and one 3d. So 1, 2, 3, 4, 5 orbitals are coming together to create 5 hybrid orbitals. And those are going to be our 5 sigma bonds. So we have 5 things coming off of it. We have the top and the bottom, and then we have 3 going in the triangle formation, which is giving us our trigonal bipyramidal shape. So here's an example. We have 5 things coming off of it. We have the top and the bottom, and then we have the 3 coming out from the overlap of those hybridized orbitals. Now finally, let's talk about the octahedral geometries. The center atom, once again, we're always concerned with the center atom when we're talking about hybridization, has 6 electron groups. Those could be lone pairs and or atomic atom groups. The molecular geometry, or the shape, is also once again dependent upon the number of lone pairs. So octahedral is what you see here. So there's 4 in a square shape, and then it becomes a pyramid. And the fact that it has 4 shapes, 4 triangles on the top and 4 triangles on the bottom, if you looked at it in 3 dimensions into a shape, you get 8 shapes total for octahedral. Square pyramidal is if we have 1 lone pair here, and so therefore all you see is the pyramid on the top or the pyramid on the bottom. And square planar is if we had 2 lone pairs here, and all you see is the square. The center atom uses empty d orbitals from valence shell for hybridization. It could also be used to make pi bonds. So let's take a look at what gets hybridized. We have 1 3s orbital, 3 3p orbitals, and 2 3d orbitals. So 1, 2, 3, 4, 5, 6 orbitals all together, blending together to make 6 hybridized orbitals. And those hybridized orbitals are what's going to give us our sigma bonds to form those compounds. So 1, 2, 3, 4, 5, 6. That's where our overlap comes in. If there were pi bonds, they would be with the unhybridized orbitals. And here's an example, SF6. Notice that there's 6 things coming off of it. There's also 3, 4, 5, invisible 1 here for 6 hybridized orbitals. So this isn't a perfect system. The valence bond theory predicts many properties better than the Lewis theory. It can tell us the bonding schemes, the bond strengths, the bond lengths, the bond rigidity. The valence bond theory does not predict, however, a compound's magnetic behavior as well as we had liked. The valence bond theory presumes that the electrons are localized in orbitals on the atoms in the molecule. In other words, they're in specific locations. It doesn't account for the delocalized electrons. And that's when we're going to introduce the molecular orbital theory, which will be in the next tutorial. With the valence bond theory, the valence electrons are localized between the atoms, or our lone pairs. Where with the molecular orbital theory, the delocalization of valence electrons are within the molecule itself. With the valence bond, the half-filled atomic orbitals overlap to form the bonds. And those were the sigma bonds, or the hybridized bonds. The valence electrons in the molecular orbital theory are in orbitals, called molecular orbitals. And they spread over the entire molecule, not just specific locations. And we will once again talk about the molecular orbital theory in the next tutorial. Bam! Last one.